Let us start with chemical equilibrium. So when we discuss about equilibrium, so it is basically of two types, that is static equilibrium and your dynamic equilibrium. Suppose we have a block and we are applying force on either sides with the same magnitude. So this block will feel no force because net force is zero, and this will remain constant as in rest position, and this is known as static equilibrium. Now when we talk about dynamic equilibrium, the equilibrium establishes during the motion. So consider a vessel here and we have made a pore inside it. So this is the pore and this is a constant water, which is basically, you can understand by visualizing it, because as here I am drawing a tap in it and water is constantly falling down, and with the same speed by this pore the water is constantly draining out. So you are seeing that this water content is constant, and here dynamic equilibrium establishes. So in the chemical reactions, basically you are studying the dynamic equilibrium. Let us start with the equilibrium and dive into the concepts deep. So if you consider a reaction, you have two types of reactions, that is irreversible and reversible reactions. When we talk about irreversible reactions, consider a reaction A plus B where these are reactants and C plus D. So these are the products, and here the alpha is 100%. Later on subsequent videos I will explain that what is alpha. This is known as degree of dissociation percentage. So this is degree of dissociation percentage, and the alpha tells about that how many part of the reactant is going to convert into the product. So here I am not drawing a reversible sign, so this denotes that this reaction will not go backward in direction. So the examples of the irreversible reactions is acid-base reactions, and your PPT reactions. For example, AgNO3 is reacting with NaCl and converting down into the AgCl, which is the PPT, and your NaNO3, and your combustion reaction. For example, carbon is combining with oxygen and converted down into the CO2 and heat. If we talk about reversible reactions, so here I am drawing a partition so you can understand it clearly. If we talk about reversible reaction, consider here is reactant and the product. So here the reaction can go forward also and backward also, but how the equilibrium will establish at a point, we will discuss it later on in the subsequent videos. So this is the condition, and the alpha is basically less than 5%. Later on we will discuss that why it is happening. If you want to clear out that where equilibrium establishes, so here is a point that strong electrolytes shows no equilibrium, as the next point implies that the equilibrium concept now, as the equilibrium concept is only for reversible reactions. Let us talk about equilibrium in detail. So here I am drawing a partition so you can understand it clearly. So let us start about equilibrium, and we will discuss that how equilibrium basically is affected. So here you can see a reaction that A plus B and C plus D, and it is having reversible sign, and of course due to the reversible sign it is having equilibrium at some point. So with time the forward reaction basically decreases with speed, and with time vice versa the concentration of product, or you can say the backward reaction, increases, and at some point both the rate of forward reaction equals to the rate of backward reaction. This point is known as the equilibrium point. So here we will understand it by graphically. This is rate of reaction, and the x-axis I am drawing time. So with the time the rate of forward reaction decreases. So here I am drawing this as decreasing, and the rate of backward reaction is increasing. This is rate of backward reaction, and this is rate of forward reaction, and this point implies that the rate of forward reaction is equal to the rate of backward reaction. This point is known as the equilibrium point. Now what happens to the concentration of reactant and product? So I'm drawing a graph here, and this is between the concentration and the time. So suppose this is the product C, this is the product C, and this is the product D. It decreases and becomes constant, right? And this is, I'm drawing just A, not drawing B. It is also will be same. This is for B, right? And the concentration of the product basically, you can see, oh, I'm very sorry, this is A and this is B and this is D and this is C. So you can see the product concentration is increasing and becoming constant. Case 2 can be also possible, that the product concentration increases with respect to the reactant. So this is the reactant concentration and this is the product concentration. Also another case is possible that these two concentration of the reactant and product become same.